Okay, so today we're talking about section 6.8. That's the only section we're going to be talking about today. And then then Thursday we'll deal with chapter 7. We'll start with that and then continue with that next week. Some things to keep in mind is exam 4 is next Thursday, so April 16th. So it'll be just like the other exam, where it'll be on Alex. Let me double check, right? Week of the 13th. So there's the exam. Now, notice that the material is going to kind of slow up, right? I'm not going to, put this all into one or anything like that. We're just trying to get caught up from the week that we lost. So it'll slow back down starting next week. But that's the plan. That's what we'll cover Monday and Tuesday. And then exam 4 will be that Thursday. Again, you can find this on Blackboard. So if you need to look at that there, I am going to try to find, there it is. Okay, so just keep that in mind. It'll be on Alex. So just like the last exam. I don't know how many questions yet, but that is where that is at. Any questions over this before we continue? Okay, make sure all my pin sizes are the same. Okay, so section 6.8, as you can see, is complex numbers. If we wanted to rewrite it up here, we could. But I kind of wanted to review. Anyone remember what we would write if we were going to take the square root of a negative number? Well, we would say that this no real solution, right? So anytime that you would see a negative underneath the square root, the only thing we could write is no real solution, right? So even if you had something like the 12th root of -2, right? Even remember, it's an even power, so again, we would have no real solution. So there's a recurring pattern, but now that we're going to learn about complex numbers, we're going to be able to actually evaluate this and give it some meaning. And so that is where section 6.8 comes in. Section 6.8 is about complex numbers, and moreover, we're going to define this I. Now, the I in this case, this shows that it is imaginary. Now, it's a shame that they use imaginary to describe these numbers or these set of numbers. Um, I think it was Gauss, one of these famous mathematicians, was disappointed. He'd said that they should have used a better word because these aren't imaginary. They have some real world applications. So imaginary numbers, they can be found. This isn't really relevant to the lesson, but it's nice to know kind of where you'll see them in circuits. Boy, I don't know if I spelled that right. Yeah, I don't know. I don't know if that's spelled correctly, but they can be found in circuits. That's one of them. Like in electrical engineering, you deal with imaginary numbers quite a bit. Um, did I spell it incorrectly? Nope. Oh my goodness. Okay. That is why it was such a warm day today. Hell has frozen over. I spelled the word correctly. Okay, so first things first, let's define what the imaginary number is, right? So here it's saying I is equal to the square root of -1. So just like before, we dealt with this yesterday, right? If I wanted to get rid of the square root, right? Remember that means there's an index of 2 here, right? An index of 2, which means what I could do is square both sides, right? And so what that means is actually I squared is equal to -1. So both of these mean the same thing, and it defines what your imaginary number is going to be. Oh, wow, that's bad. The other definition that we have below is talking about if b is positive, a positive real number, then the square root of negative b is just I times the square root of b. Right? So again, if we had something like -2, or the square root of -2, what it's saying is, right, 2, 2 itself is greater than 0. So then we can think of this as I square root 2. So any questions so far? Okay. Well, now let's look at our square root of -64. So above we said there were no real solutions, and it's true, there is no real solutions. What we're going to have is an imaginary solution. So let's look at it. Let's recall, just because I scrolled down, that we have I squared is equal to -1, or the square root of, oh, hold on, let's write it like this. Let's write it as I is equal to the square root of -1, right? So we're gonna keep this in our toolbox today, and we're gonna use it quite a bit. Okay, so let's evaluate the square root of -64. Well, how we can think about that is you can have the square root of -1 times 64, right? And then we know what the square root of -1 is, right? We've said that is I. So you could, um, again, this is now I square root 64, and then the square root of 64 is 8. So we're going to have 8I, like so. Now, this example here is the opposite of the square root of -4. So let's have -1 times the square root of -4. Right? Let's make sure we know that -1 is out in front of the square root. Again, now that we have a negative underneath the square root, right, this -1, it's always good to, be aware that that -1 is multiplying a +4. So this becomes -1 times I times the square root of 4, which is -1 times I times 2. So each step down there, we're breaking it down, right? So this right here, the square root of -1 is now I, and the square root of 4 is 2, right? The -1 was just out in front at the very beginning. So when we combine all those together, we get -2I is where our solution is. Any questions over just the introduction of I, or the square root of -1? No, hold on. Let's do this one, and then I'll go back and I'll nerd out a little bit, and we can see kind of some more information about uh, imaginary numbers in general. Okay, so we're going to carry this down. I'll drop it down here. So again, remember that, move this down just a little bit more, that whenever I have this question 1 of 6, that means that this here is similar to your daily work number 1. So the numbers will probably be different, but the method to solving them and the problem will look pretty much identical to this, taken from Alex. Again, I'll have it timestamped in the video when I upload it. So if you go to the video and the description or the comment section, you can just click the time and it'll take you to here if you want to review. Okay, so yeah, again, we gotta, write in terms of I. So again, we're gonna have the square root of -1 times 80. Now, the square root of -1 is I, so that means this is now I times the square root of 80. So this is a review now to be able to simplify the square root of 80, which I think it's a good problem to look at. So looking at the square root of 80, or just 80 first, let's break it into its prime factorization, or you're looking for its prime factors, or you're looking for its perfect squares. So when you break that apart, 240, um, well, 5, 8, 2 and 4, 2 and 2. Okay, so we got 4 2s and 1 5. So that means 80 is now can be rewritten as 2 to the fourth power times 5. Okay, 2 to the fourth power. Now this seems kind of redundant to kind of go backwards, but this is another way to look at this example here. 2 to the fourth, which is 2 squared, the quantity squared, right? Or it's 16 times 5. Now you're probably wondering why I wrote all of these equivalent ways of just saying 80. Well, remember that you're looking for your perfect square to take out of 80, right? To break apart into 80 and then evaluate them separately. So now what we have is the square root of 16 times 5. Move down just a little bit more. And so we have the square root of I. Now, you can separate this, right? Remember, this is 16 times square root of 5. So we know what the square root of 16 is. It is 4, so we have 4I times the square root of 5. You could write it as, like, here, let's do it like this. I like to keep the imaginary part, which is I, um, your imaginary, what's classifying as an imaginary is the letter I, and then 4, right, is your real number here. So you could write it as the square root of 5 times 4I, like that. You got to make sure that you know that your square root of your radicand doesn't include this 4I, right? That it's just this. So this is the common way of writing that. Are there any questions over question type 1? Seem okay so far? It's introducing, again, just being able to evaluate these negative square roots, and they come out as I. Okay, so something to keep in mind, that this is a definition that we had, and it's saying that if A and B represent real numbers, such that the nth root of A and the nth root of B are both real, then you can separate them. The reason that this is important is uh, this was an old definition that we had, but it's telling us that we can't write the square root. Let's go um, -2 times -8. That we can't express that as square root of -2 times the square root of -8, right? So you can't separate them if it's negative underneath the square root, right? We could separate it here because we're looking at a positive 80. So that's just an important thing to notice there with that. Okay, before I continue on, I think it'd be kind of neat to look at just the imaginary numbers, and you can look at a graph of them. It was something that I enjoyed learning about that I didn't really know too much about. So, um, right, this won't be on the test, but I just think it's fun. So you've got X and Y, right? This was our coordinate plane, right? You've got your X-axis and your Y-axis. So this is considered your real plane, right? We'll get to real numbers here, but it's saying that if you had a point like 1, 2, right? There's your point. They're both real numbers. 1 and 2 are. But the the complex plane, there's a really good video series on it on YouTube. So if you'd want to learn more about it, they've got really good graphics, a lot better than what I'm drawing. Imagine that you've got your y and x axis. Well, to look at where the imaginary numbers are, think about that you're picking up the x axis, right? So if this is your x axis, right? I just can't see that you're that you're coming towards you in the screen, that your imaginary numbers are actually coming out of this x axis. So what we in the complex plane, you can graph it as the real part and the imaginary part. So, I mean, that's all we're going to do. We're not actually going to graph imaginary numbers, but just know that there is a way to graph them, right? It was something that I had never really thought about, and then I saw the video on YouTube, and it was very interesting. Okay, so I'll get down from. I would even call it a soapbox. I just thought it was interesting. Okay, so I'm gonna move back down. So we have that property. Um, yeah, so we need to evaluate these right here, right? So again, this is like your second daily work problem. Um, Now, it'd probably be good to work these before we do the daily work problem. Wait, so then how do we do this, right? If we can't separate them, well, remember that you can rewrite it as -1 times 100 divided by -1 times 25. So again, the square root of -1 is I times the square root of 100, and you have I times the square root of 25, right? So um, again, the square root of the negative is where this imaginary part is coming from. Okay, so now we evaluate the square root of 100, so we get 10 times I, and then the square root of 25 is 5, so we get 5I. Here we have a nice cancellation. We've got I over I. So I over I divides to 1, right? You can think of it as, that. So that goes to 1, and we're left with just 2. Going on to the next one here, it's similar to the one up above here, where you're going to have the square root of -1 times 25 times the square root of -1 times 9. So I'll drop the equal sign down here. Right, again, there's your imaginary unit, which is 25, and 9. I square root 9 is your imaginary unit. We'll move this down. Okay, so just to keep with it, right, that is where your -1 is coming. When you take it out from the square root, it becomes I. It's how you evaluate a negative, or the square root of -1. Okay, so this is now 5 times I. This here is 3 times I. Okay, so now we've got 5I times 3I. So just like if this was an x, we would have 15I squared, right? I times I. But remember what uh, remember what I squared is, right? So remember that we've got the square root of -1 is I, and then we also know that I squared is equal to -1, right? So actually, this is going to equal -15. Or here, let's do it like this. 15 times -1, right? Again, this I squared is now -1. Right like that too. Any questions over this one? Okay, I'm gonna move down just a little bit. and then we'll work through the daily work problem. Okay, so it's good to just have that with you at all times, so you remember the properties. All right, so if we had the square root of negative 48, again, write it as negative 1 times 48. Really, anytime you see a negative underneath the square root, it can come out as I. So separating like this isn't necessary, just it's a good reminder. So now we've got I times the square root of 48 and I times the square root of 16. Okay, so now at this point where you don't have a negative underneath the square root, you could combine them back together, right? You could look at what the square root of 48 divided by 16 is. Or you could evaluate them separately. So in this case, I'll probably just evaluate them separately so we can see it worked that way. So your i's divide out, right? I over I. And the square root of 16 is 4, right? So now we have to simplify 48. We need to reduce that. So let's do that real quick. Here's our next example. Okay, so little scratch work over here is, where do I want to work this at? Let's look at 48. We'll break it apart into the prime factorizations. Again, we're looking for perfect squares, right? We want to know what a perfect square is from 48. Any guesses right now while I move this down? Right, what do we think a perfect square could be? So you could start breaking it apart, right? You could do 2, and this would be 24. Again, 2 and 12, 2 and 6, 2 and 3. Okay, so notice 2 times 2 times 2 times 3, that 48 is 2 to the 4th power times 3, right? Okay, so when we plug that back in, right, we're going to have the square root of 2 to the 4th times 3. Now, once we're here, we know what the square root of 2 to the 4th is, right? Because remember that this can be written as 2 squared raised to the 2nd power, right? You can raise that power up there. And so when we do that, right, we could separate it. And you have a nice cancellation there, right? So you have 2 squared times 3 divided by 4. Again, this is now 2 squared is 4. So 4 square root 3 over 4, which you can divide the 4 over 4. Right, remember that the number, the radicand, or the number underneath the square root, you can't simplify, right? It's a number, we leave it there, and then work down that way. Are there any questions? I worked that a little bit differently than I did the one up above. There are a lot of different ways to approach it. Okay, so carry it down here. Go down to about right here. Okay, so, oh, hold on. Hold the phone. It's hiding from us. Okay, so working this problem here, we only have one negative right now, right? We've got the square root of 4 times the square root of 9. So let's just rewrite it, and then we'll start evaluating. So we know that the square root of 9, or negative 9, can be written as 1 times 9. So the square root of 4 is 2. Now we have a negative 1 underneath the square root, so it can come out as 1. So we now have I times 9, which the square root of 9 is 3. So we've got 2 times I times 3, right? Or 6I would be what that one is. Any questions before we go on to section 2? Okay, we're going to move on. So section 2 is talking about the powers of I. So we're not distracted by this. Move that down just a little bit further. Okay, so we know from the definition, I is equal to the square root of -1. So again, that is equivalent to saying I squared is equal to -1, right? Same thing. So what it's saying is we could list out our powers of I and hopefully start seeing a pattern, right? So if we had, real quick, what is I to the 0 power? What is anything to the 0 power? Do we remember? Anything to the 0 power is what number? Anyone in the chat? 1. Good, thank you. Yeah, so I to the 0 power is 1. That really didn't help us a whole lot, but let's go I to the first power. Well, I to the first power is I. Now, going up here, I squared, which again is I times I. Well, that is now -1, right? Just by our definition of what I is. Now, I cubed. Now, I cubed is I times I times I. So here we've got I times I, which is -1. Multiply that by I again, because we've got 3 i's. We get -I. Okay, so I to the 4th. So now we've got 4 of these i's we're multiplying together. Anyone want to take a guess of what the 4 i's multiplied together would give us? What do you think here? This to look more like a chart. So. Okay, so what we would get is 1. Now why? Well, right, this is -1. Now here, this is also -1. So -1 times -1 is just 1. Okay, so let's just, for the joy of it, go up to I to the 5th, and we'll see what we get. Okay, so we've got I 4 times, right, multiplying by each other, and then we've got another I. Okay, so we said this right here, I to the 4th, which is I times I, is 1, right? We just showed it up above. So actually what we see is we start repeating. So all of your unique values, call them unique, right? But the powers 1 through 4 give you all of the values you're going to get. They just start cycling over again, right? So actually I to the 6th, if we multiplied all that out, would be -1, right? Where you've got those different powers there. We keep going. So the thing, what I would say to take away from the powers is knowing this property here, we can just classify what each of these are. So I would say knowing up to the 4th power, which again, you can just calculate by multiplying I a bunch of times. Any questions over how we do that? Okay, so to simplify higher powers of I, basically you can break apart your expression into multiples of 4, right? Because that'll just reduce to 1. And then write the remaining factors is I squared, and I to the 3rd, right? And again, we know what those values are, right? Those are good values. So instead of having to repeat this over and over again to figure it out, we can just use the pattern and then do it that way. So I'm going to move down just a little bit here to I to the 18th, right? So to decompose this, recall, what we would do with something like 2 to the fifth, right? That means 2 times 2 times 2 times 2 times 2. Well, we can also rewrite this as 2 squared times 2 times 2. Now, it's just a different way you can write it. Like, you could also write it as, 2 times 2 squared times 2 squared. The point is just saying that you can break apart, this exponent into a bunch of littler exponents, right? Just to get what we want. Because really what we want to do is decompose it so it's I to the fourth, and then whatever else it could be. So let's look at this example here. I to the 18th. So what we would have here is, the question is, can we somehow get, let me put a little space here. All right, we want to know, can we break this apart so we are raising it to the fourth power? Because again, these two multiplied together should give us 18. Um, what do we think here? Well, the question now is, what this is saying is 18 is equal to some number times 4. Well, when we divide that, it doesn't come out evenly, right? 18 divided by 4 doesn't come out to a nice integer number. So we can go one lower, right? Well, if this was 3, hold on, let me go back, right? Um, Hold on. So it doesn't divide it evenly, but if x is equal to 4, well, then we get up to 16, so we're almost there. So if we have I to the fourth power, that means we need I to the what power? So someone in the chat, help me out. It's going to be I to what? Remember this is, I to the 16th power here. So what would my exponent need to be here so I get 18? Do we see that it would be 2? Because again, what this is, what these exponents do is when you're raising to the power, what we have here is 4 times 4 plus 2, right? That is equivalent to what these exponents are doing here, right? So being able to dissect 18 down using our exponent rules to get to this. Okay, so let me scroll down just a little bit more. Separate it. Okay, so now what we have here is I to the fourth is 1. I'm going to move this down just a little bit so we can see it a little easier. I'm actually right here. Right, so I to the fourth is 1, and it comes from this property here. So that now is 1 raised to the fourth power times I squared. So anything, or 1 to any power is going to be 1. Now I squared, on the other hand, is going to be -1, right? And that comes from that property there. So what we end up here with is -1. So I to the 18th, I to the 18th power is -1. Okay, before I move on to the daily work, we go out of order here, but it's just how the book had it. Are there any questions? Okay, well, let's look at the next one, and we'll see how we're doing here. So I'll move it down just to right here. I don't know if I can't erase that. Okay. All right, so now we have I to the 25th power. So again, we're wanting to dissect 25, right? We want I something up here. Oh gosh. To the fourth power, right? Now that might mean that we have another I over here, right? We're not quite sure, right? It's just note that it is odd, right? So we probably will have something left over that we'll have to do. Now, right, the number that goes here should multiply to get us to as close to 25 as we can without going over, right? So good, it would be 6, right? So that's not orange. So the number, oh gosh, yeah, I don't know why it's not working. Okay, whatever. Right, this would be the term to get it to work. Yeah, it would be I to the 6th power, right? Because now this gives us 24, right? 6 times 4 is I to the 24th, and so that means our remainder here is going to be to the 1st power, right? Probably a better way to look at this would be swapping these. I think it makes it easier to see what's going on. It's still the same thing. We'll talk about it here, right? We want to know I to the 4th power, right? That's our property. Again, it's going to be 6, but it's okay to write it like that because your exponent rule, which I don't know why I can't get this stupid thing to work. Hmm. Right, that if you have a to the nth power raised to the mth power, that's just going to be n times m. So that means that you can rearrange it, right? You could have a m times n and then raise that there. So it was okay for us to swap it around. We didn't have any issue there. So again, we now have, I don't know why none of it's working. This right here is 1, so we've got 1 to the 6th power, and we've got I to the 1st power. So moving down a little bit further, this is 1 times I, or just I, like that. Okay, before I continue, uh, any questions over this type of example? No questions? We're good? Okay, we'll move on to the third section, which is the definition of a complex number. So above what we defined, what the imaginary I was, right? So here we're actually going to define what a complex number is, which is what this section is referring to. So I'll move down to about right here if you're still copying that above. So we've got a nice book definition. So a complex number is a number of the form a plus bi, where a and b are real numbers, and I is the square root of -1. So to recall here, what real numbers are, right? Real numbers could be like 1, 1/2, -3, square root of 2, 0.3, repeating that, right? So a and b could be any of those sort of numbers, which are real numbers. And then we have to have that special property of I, where it's saying I is equal to the square root of -1. Again, that's just equivalent to saying that I squared is equal to -1. So those two mean the same thing. Okay, so going down a little bit further, let's start with some definitions here. So there's important things to keep in mind that if b is equal to 0, right, so here, then it's a real number, right? So that means an example is saying that if you have 3 plus 0i, well, 0 times anything is 0, so we get just 3, right? So if b is 0, then it's a real number, right? Our imaginary unit goes away. You can think of it as this is your real part. Oops. Real. This is your imaginary part. So the complex number it just has both real and imaginary parts. Ooh, okay. I'm unsure about that, but I think imaginary comes in a little further down. Okay, right there. Yeah, so again, if b is not equal to 0, then a plus bi is an imaginary number, right? So if we looked at that, that's saying that if you had 2 plus I, right, it's imaginary. Right? You have an imaginary part to the number. Okay. The complex, oh, we'll go a little further down. Oh, okay. This whole video lecture is me just trying to figure out how to move this little box here. Okay, the complex number a plus bi is said to be written in standard form. So when it wants you to write a complex number, it wants you to write it in this form here. This is the standard form for a complex number. So a plus bi. The quantities a and b are called the real and imaginary parts, respectively. So kind of talked about that up there of a complex number. The very last thing is it talks about the conjugate. So the complex numbers a minus bi and a plus bi are complex conjugates. And we'll see why that's so nice, why we care about the complex conjugate further down when we start dividing. But for right now, there's just some important information about that. What's kind of interesting about complex numbers is remember when we talked about the real number, oh gosh, still in the highlighter. Remember when we talked about the real numbers? The real numbers were broken up into two separate categories. They were broken up into the irrational and rational, right? Now we could go further down because within the rationals, you have the integers, right? Again, the rational numbers are referring to fractions, right? Like 1/2, 3/2. Then if you went a little bit further here, you have the integers, which are all the positive and negative numbers. Then you've got the whole numbers. So integers are -1, -2. We'll see why I'm filling all this out. The whole numbers are the positive numbers, including 0. And then you've got natural, which is just 1, 2, 3. Anyway, so there's your real part. Well, actually, we now have a second box. And that second box is the imaginary numbers, right? So that means like 3i square root of I times square root of 2. That's where square root of 2 would go. Pi would go. Yeah, like -I, right? That's where the imaginary is. Well, what a complex number is basically all of these. So your complex number is all of this is within the family of complex numbers. So before we had this kind of separation between rational and irrational, which actually let me get rid of it like that. Kind of weird. Okay, yeah, so rational, irrational, but then we had the imaginaries. Well, inside of this whole bubble here, uh, these are all a type of complex number. So we've just learned the general, that all these different numbers that we've worked with are all a type of complex number, which I thought was kind of neat. So I thought everybody would like to see that. Okay, so there's that little nice drawing. Move it to right here if you still want to copy it down. Okay, so now we're going to move on to the fourth section. So the fourth section is adding and subtracting complex numbers. Right, so we've just defined what a complex number is. Remember, just so we have the definition, a complex, oh, hold on, let me write like this. So a complex number is written in the form of a plus bi. Right, so there is your type of the standard form for a complex number. So now we're going to learn how to add, subtract, divide, and multiply these. Okay, so I'll move down to about right here. So here we have the square root of -8 plus the square root of -18. Okay, so just like up above, we're going to have to evaluate these and add them together. So we're kind of reviewing the idea of adding just plain radicals together, right? We wanted the radicals to be like radicals is what the book called them. Okay, so again, just so we have this for reference, I squared is -1, which means I is equal to the square root of -1. So nice little thing to keep tagging along here. Okay, so this will be our blue, this will be our orange. Okay, so our blue, right, is -1 times 8, and the -18 can be written as that there. Okay, so again, we have a -1 underneath the square root, so this is the same thing as square root of I times 8, and this is I times the square root of 18. Now notice we can't add these together yet because we don't have a like radical. So we need the index to be the same as well as the radicand. So probably good to note that if you wanted to add the square root of n plus a, I'm going to make it to the nth power, right? If you wanted to add this, you would have to have the same thing, right? So then this is 2 of those put together. I made it look kind of worse than it needed to be, but it's just saying that you can add these two together, right? It's the idea of it being a like radical. Okay, so we need to evaluate this. Well, remember that 8, right, is 2 and 4, right? So if 8 is equal to 2 times 4, our perfect square is 4, so 2 times 4. That means that we're going to have 2i times 2, times the square root of 2, right? With this 4 coming out as positive 2, right? Our square root of 4 coming out as positive 2. 18, on the other hand, can be rewritten as 2 times 9, right? Our perfect square is 9. So we get 3i times square root of 2. with your square root of 9 coming out as positive 3. Okay, so notice now we can add these together, right? We have an index of 2 and a radicand of 2. So we have square root of 2 for both. So when we combined, we add the 2 and the 3, so we get 5i square root 2, right? The i's, you can think of it as one thing, right? Think of it as 2x plus 3x, right? 2x plus 3x is 5x. So 2i plus 3i is 5i, right? And we still have our square root of 2. Any questions over this example? Again, I skipped the work here a little bit on simplifying the radicals, but hopefully you're feeling pretty comfortable with that. You have until tomorrow to get the daily work done in regards to this. So if you haven't done that yet, make sure you're working on the daily work due tomorrow. Okay, so here we've got, now we're subtracting them. Okay, so cosine. Now, just like we had when we were subtracting two quantities, right, you want to make sure to distribute your negative sign, right? So we've got a -1 out in front, so you want to distribute that to both of those, the two terms here. So you get -6 plus 11i. -1 times -9 is a positive 9. -1 times -12i is a positive 12i. Right? So now let's combine the real parts with the imaginary, or the real parts together and the imaginary parts together. So we got -6 plus 9 plus 11i plus 12i. Right? So I just putting the real parts together and the imaginary parts together. Ooh, looks bad. Okay, so that is what we did there. We just rearranged the terms. So when we add these together, -6 plus 9 is a positive 3. Now 11i plus 12i, same thing as 11 plus 12, right? Just keeping the I with us. So that is 23i. And that there is your solution. Any questions? Can you guys hear my dog barking in the background? Okay. Good. Yeah. I think he's barking at me because he forgot I'm down here. That's probably what he's doing. Okay, so let's look at this example here. So again, this is like your third daily work problem. We need to add these two together. Well, what's nice is notice that it's already nice and simplified, right? We have no radicals we have to worry about. We just have our real and our imaginary part. So when we have something like this, right, we can recopy the problem down. So I want to combine my real together, right? So this is -2 plus -4. And then let's go ahead and do the imaginary part together, right? We're just adding, so we can move our terms around. So plus 6i plus 2i. That's going to give us -6 plus 6i plus 2i. 6 plus 2 is 8, so 8i. And that right there is your complex number in standard form, right? Your imaginary part being second. Okay, so move down just a little bit to here. Now we're going to talk about multiplying complex numbers. Okay, so multiplying complex numbers is just like if you wanted to multiply any two binomial expressions together, right? You're going to distribute or FOIL them together. So let's look at the 10, right? And we're going to distribute the 10 to the 2. and to the 3I. Okay, so that means we're going to have 20 plus 30I. In a similar manner, we'll take our negative 5I and we'll distribute to our 2 and positive 3I. So we get a negative 10I. Now here, it's a little interesting, right? We've got, I think it would be best to show it mm, negative 15I squared. Everyone okay with that? Let's keep in mind where that came from, right? So negative 5I times 3I, right? So our negative 5 and 3 are multiplied together to give us 15, and then our I and our two i's are multiplied together, so we get I squared. But in the chat, what is I squared? What is I squared equivalent to? Anyone know while I rewrite the property? Good, negative 1, right? So it's good to keep that there, right? It's in our toolbox. So we've got 20 here. Well, hold on. Before we do that, let's work this part out here. So negative 15 times negative 1, right? So the negative 1 came from this I squared, right? So negative 15 times negative 1 is a positive 15. So I'm going to go ahead and just rewrite all this out again. Positive 15. So we have 15 and 20. We're going to combine our real parts now. We'll go ahead and show some work here. Down below, I might not show as much, but it's probably good to look at all the steps here. Okay, so 20 and 15 is 35. And 30I minus 10I is a positive 10I, or 20I. So that there is your complex number in standard form. Any questions over this here? Okay, moving on. We've got a daily work problem. Now, right, it's pretty similar to the one up above, but we'll take a look at it here. So we've got negative 2 minus 3I and 4 plus 3I. Right, so again, we need to distribute these. So take I, or negative 2, and multiply it to those. So negative 2 times 4 is negative 8. Negative 2 times 3I is negative 6I. Now negative 3I times 4 is going to be negative 12I. Now here, negative 3I times positive 3I is going to be a negative 9I squared. Right? So continuing on here, we've got, I'm gonna go with black. We've got negative 8 minus 6I minus 12I. Now here, this is going to be a positive 9. Now why? Well, it's because, again, I squared is equal to negative 1. So that means we have negative 9 times negative 1, right? That is from there. So we get a positive 9. So now we can rearrange our real parts with our imaginary parts. So let's put our reals together. So negative 8 and 9. And now the imaginary parts. We'll even use the real colorful one because it's our imagination, you know. It was a bit of a stretch, but I thought I'd go for it. Okay, so combining these together, negative 8 plus 9, or 9 minus 8, is 1. Negative 6I minus 12, right? You're at negative 6, but you're taking 12 away, so you're going super negative. You get negative 18I. Now keep in mind that it wants it in standard form. Good, thank you. It wants it in standard form. So I'm just guessing that Alex won't doesn't want it reported as negative 8i plus 1, right? It's not standard form. It's correct. It means the same thing, but it's not in standard form. So keep that in mind. Okay. So that's all I have to say about that. Standard form, my goodness. Can you imagine if I was teaching you English right now? Or like vocabulary and I had to write? Oh, that'd be bad. Okay. So continuing on here, move down to here. So now we're in the last section, which is division and simplification of complex numbers. So I want to recall, well, hold on. Right. Okay. So can't remember if I had an extra problem here I wanted to work. We're not going to. Okay, so we got 5 plus 2i. Let's put some parentheses around those. Now, if I wanted to, or not if I wanted to, but what is the complex conjugate? So recall about the complex conjugate. Okay, so with the complex conjugate, let's say you had a plus bi. Well, the conjugate of that is going to be a minus bi. So remember back from last lecture where we talked about the multiplying by the conjugate when it came to a radical, right? It means you just change the second sign to be a negative. And so here, right, the conjugate is that one there. Or I guess if you had that, it would be the other one. But now let's go ahead and multiply this by the complex conjugate. And we're going to see like why it's so nice, right? Why the complex conjugate is nice. And let's title it that, why the complex conjugate. Okay, so moving it up here, leaving them behind. Okay, so let's multiply by the conjugate, which we said was 5. We got 2i, but we have a negative now. So instead of a positive 2i, we have a minus 2i. Okay, so yeah, let's take a look at like, well, why is this one so nice here? Why do we worry about the conjugate? So take 5, we're going to distribute our positive 5. So we're going to have 25, 5 times 5, and negative 10i. All right, multiply 5 to negative 2i. Now here, we've got a positive 2i. We'll distribute that. So it's going to be a positive 10i times a negative 4i squared. Okay, so we've got, move this down just a little bit real quick. Now, why the conjugate is so nice is, again, we have the same but opposite, right? So we have a middle term here that goes to 0. So we have no more imaginary part there. So we have 25 plus 0. Here is negative 4 times negative 1, because I squared, again, I'm going to get that tattoo of I squared equal to negative 1. So I've just always got it right there, right? I can always look at it and be like, negative 1, right? So that is what you get. So the reason the complex conjugate is so nice is if you want to, not have an imaginary number, you can multiply it by its, complex conjugate, given it's in this form, and you end up with just a real number. Oops, see if I can add correctly, 29. Are there any questions over the complex conjugate before I go on to why we worry about it? But that is why the complex conjugate is so nice, is we multiply them together and we get rid of the imaginary part. Okay, so that brings us to here, dividing by a complex number. So what we want here is uh, um, we want it to be an a plus bi, right? We want a standard form, right? That's our goal. So we need to somehow get all of our real parts here and all of our imaginary parts, or be the other way for you guys. No, nope, here. Real parts here and imaginary parts there, right? Okay, so to do that, we can multiply by the conjugate. So when you have this fraction here, multiply by the conjugate. Really, it's the complex conjugate. So we're going to multiply by 5 minus 2i. And since we did multiply it in the denominator, we also have to multiply it in the numerator. Let me get this a little more straight here, level. So that, and then 5 minus 2i. Okay, so we have done the work up above, right? 5 plus 2i times 5 minus 2i. So what we have now is 4 minus 3i times the quantity of 5 minus 2i, all divided by 29, right? This here was worked above. We'll have another example just to get some extra practice here. Now, here we have to multiply this out. So I'm going to go ahead and draw this down here. We'll do 29. Now, let's do some scratch work. So we're not distributing all of that, you know, in fractional form. Okay, so 4 minus 3i times 5 minus 2i. So again, distributing this, we'll have 20 minus 8i and negative 15i plus 6i squared. So again, multiplying those together. This right here, negative 8i minus 15i, is going to be a negative 23i. Oh, I. This is 6 times negative 1. This is 20. So we have 20 minus 6 minus 23i, right? So there's your negative 6. We subtracted 20. So we've got what? 20. Oh, we've got 14 minus 23i. Okay, so we put this up here. 14 minus 12, goodness. 14 minus 23i is your simplified answer. But wait, you're probably thinking, well, wait a second. That doesn't look like it's in standard form. Well, keep in mind, this is going the extra mile. But remember, you can separate this fraction, right? So you've got 23 over 29i. So there it is in standard form. Personally, I'm okay with this one up here, but you need to make sure that if you can simplify it, you simplify it further, right? So 14, 29, and 23, there's no numbers they have in common. You won, but that doesn't, lower the values any. Okay, so either one of these would work to do that simplification. Okay, so we've got the very last daily work problem. And we'll take a look at this, right? So again, we want to write our complex number in standard form. So let's go ahead and rewrite what we have. So 6 minus 5i divided by 2 plus 3i, right? So to get rid of this imaginary number down in the denominator, which is what we want to do, we need to multiply by the complex conjugate. So be thinking of what is the complex conjugate here. Get this rewritten. Okay, so the complex conjugate is 2 minus 3i. Again, you just take that second number, right? You change the sign on it, you have the complex conjugate. If you multiply in the numerator or denominator, you have to multiply in the numerator. So multiply quantity 2 minus 3i at top and bottom. Okay, so here we are. Now we've got a couple things to evaluate here, right? I would say work these separately. So over here, I'm going to do 2 plus 3i times 2 minus 3i, right? I'm going to work that out, and then I'm also going to do 6 minus 5i times 2 minus 3i. Okay, so again, multiplying this out, we might as well use some colors here. 2, distribute to both of those, you get 4 minus 6i. Now distribute 3i, you get a positive 6i and minus 9 times I squared. Right? Again, recall what I squared is, right? I is equal to the square root of -1, so I squared is equal to -1. Right? So I squared is -1, so that means I'm going to go ahead and just use all these colors now. 6i, oh gosh, we've got 6i, or negative 6i plus positive 6i, and then -9 times -1, right? So this is now a -1. So these go to 0. So we got 4 plus 9. Well, I should do that in 2 steps maybe. -9 times -1. So 4 plus 9 is going to be 13. Okay, so there is one of our values. Let's go ahead and distribute this here and see what we get. So in a similar manner, take 6, distribute that to each one of those. So you have 12. These two multiply together. 6 times -3i is a -18i. And now we'll take our -5i and distribute to both. So -10i plus 15i squared, right? So now we can add our these two middle terms together. So -18i minus 10i is a -28i. Here we got 15i squared. Okay, so 12 minus 28i. This is now a -15i, right? I squared is -1. Okay, so combining the real parts, we got 12 minus 15 minus 28i. 12 minus 15 is -3 minus 28i. Okay, so we've simplified it down to these two quantities. So here in the denominator, because we multiplied by the complex conjugate, we now have 13. Up here in the numerator, we distributed those, and we got -3 minus 28i. Now again, we can't simplify any of these. And if you're not sure if you can reduce these fractions down, split them up. Say, well, does -13, or excuse me, does -3 over 13 reduce? And does -28 over 13i, does that reduce? The answer is no for both. Oh, you guys catch my mistake here? Extra negative in there. Okay, and so that right there is your complex number in standard form. Go ahead and box that. I don't know if Alex would, it shouldn't mind between those. Okay, and that does it for today. Are there any questions up to this point? Questions, concerns? Any praises you'd like to give me or constructive criticism? What kinds of dog do you have? 2 dogs. One of them is a little Chihuahua. He is, I heard he's going to be 9 or 10. He's super old, but he's like super small. He was actually sitting in this chair next to me, but he left because the younger one, you're welcome, the younger one is like a mix. He's like part Chihuahua, part like terrier, maybe. I don't really know, but yeah, he's crazy. He's the one who's barking. He barks at everything. He forgets I'm down here, so when I say something, he freaks out and barks. I'm like, but I'm down here, and then I go up and he whimpers. He's like, oh, I forgot. So he's like 2 or 3 or 4 or 5. I have no idea how old he is off the hand. Yeah, so if there are any questions, you can ask them now. If not, we will be here on Thursday covering sections out of chapter 7, which deals with solving, um, yeah, more like solving equations. Oh, hold on, there's a dog. Look. Oh, that is a cute dog. Yeah, dogs are pretty great. I didn't get a lot of work done today because the dogs were down here.
Yeah, I don't get a lot of work done any day. She always wants to be in my lap.
Yeah, it's a tough job being a dog.
Yeah. See you tomorrow or see you Thursday.
Yep, sounds good. Have a good night.
You too.
Thank you. Oh yeah, always blame the dogs. All right, goodbye. Guys, keep in mind that your daily work from last week is due tomorrow, and then this daily work will be due on Sunday. So the deadline should all be on Alex and Blackboard. So just let me know if you have any questions. Go ahead and turn the recording off.